Amid fine, dark dust particles lies a flexible organic polymer compound, rich in nitrogen and oxygen, with a unique structure often compared to a kind of space chewing gum. This discovery has sent shockwaves through the scientific community, revealing a strange and unexpected material found on the asteroid Bennu. Laboratory analysis produced astonishing results. 15 out of the 20 amino acids essential for life were detected. Even more remarkable was the discovery of all 5 nucleobases essential to the structure of DNA and RNA. For the first time in history, scientists confirmed the presence of ribose and glucose sugars directly on an extraterrestrial object. This finding demonstrates that the fundamental building blocks of life can exist on bodies beyond Earth. Could these prebiotic particles be the key to unlocking the origin of life on our planet? Let us begin a journey backward through time, following the trail of asteroid Bennu to uncover the true origins of life itself. Bennu is only about 500 meters wide, shaped like a slowly spinning top drifting through space, with a dark, rugged surface. Spectral data, mineral analyses, and return samples show that Bennu belongs to the B-type class of asteroids. Carbon-rich objects containing primitive material formed roughly 4.5 billion years ago, nearly at the same time as the birth of the solar system. Classified as a carbonaceous asteroid, Bennu is rich in carbon-bearing compounds and light elements, materials that are among the most vulnerable to destruction under high temperatures or intense pressure. Analysis indicates that Bennu has never been heated beyond a few hundred degrees Celsius throughout its history, a low enough threshold for many complex organic compounds to survive over immense spans of time. Bennu is not a solid rock, but a rubble pile asteroid, a loosely bound collection of rocks, dust, and debris held together primarily by weak gravity. Its low average density and surface observation suggest that Bennu contains many internal voids. This structure indicates that Bennu is the remnant of a much larger parent body that was shattered by a collision in the past and later reassembled gently. More importantly, Bennu avoided violent transformative processes. There was no pressure high enough to recrystallize minerals, and no internal heat to erase its original chemical memory. The choice of Bennu for a sample return mission was not accidental. NASA needed a target that both represented primitive material and was close enough to be safely reached and sampled. Bennu met multiple criteria at once: an orbit that closely intersects Earth's, a rotation period, and shape measured with precision, a surface rich in exposed fine material, and most critically, a low impact risk during the mission time frame. These factors were not only engineering considerations, but also ensured that the collected samples would faithfully preserve Bennu's chemical history, free from contamination by complex geological processes or by Earth's environment before sealing. Compared to meteorites that fall to Earth always altered by heat, pressure, and atmospheric water, Bennu allows scientists to access material that has never undergone biological contact. This fundamentally changes how data are evaluated. Instead of inferring from disturbed fragments, science now holds a true reference sample of primordial material for the first time. Bennu is small, fragile, and easily broken. Yet it is precisely this fragility that allowed it to endure as a cosmic archive. Earth, by contrast, is powerful, dynamic, and energy-rich, and as a result, its earliest memories have been erased. When we look at Bennu, we are not merely observing an asteroid, we are seeing a version of Earth's past that has been lost. This forces science toward humility. To understand our own origins, we sometimes must seek out worlds that never truly grew up. And as the samples are examined more deeply, another truth gradually emerges. Within Bennu's structure are clear signatures of water and past geochemical alteration, minerals that could only have formed when liquid water was once present. At this point, Bennu reveals clues about a larger, wetter, and more complex parent body from which it originated. Here, the evidence is no longer speculative, but mineralogical concrete records of a wet history etched into the dawn of the solar system. When the first mineralogical data from Bennu were systematically analyzed, they revealed that Bennu once carried the imprint of liquid water. Not surface oceans or frozen ice, but water that directly participated in chemical reactions deep within the material that makes up this asteroid. Hydrated clay minerals, most notably serpentine along with phosphate and pyrrhotite, are far more than dry names in a mineral classification chart. Serpentine is particularly significant because it forms only when silicate rock reacts with liquid water under relatively low temperatures, typically below about 300 to 400 degrees Celsius. This is not a reaction that happens instantly. It requires time, stable water, and a suitable chemical environment. A small asteroid like Bennu, with a diameter of only about half a kilometer and extremely weak gravity, could not generate or sustain such conditions on its own. This leads to a logical yet groundbreaking conclusion. Bennu is not where these minerals formed, it is their inheritor. The material that makes up Bennu was once part of a much larger body, either a protoplanet or a primordial asteroid at least more than 10 kilometers in size, large enough to retain internal heat and allow liquid water to exist over long periods. The presence of phosphate, an element rare yet essential to Earth's biology, plays a central role in ATP, the energy currency of cells, and in the backbone of DNA and RNA. In space environments, phosphate is difficult to dissolve or become chemically active without the presence of water. Finding phosphate bound within minerals on Bennu indicates that water-driven processes persisted long enough to reorganize elements, enriching the chemical environment in an ordered, non-chaotic way. This is evidence of an active geochemical system, not a random environment shaped solely by impacts. Alongside this is pyrrhotite, an iron-rich sulfide mineral that typically forms in reducing environments where free oxygen is extremely limited conditions consistent with the early solar system. The coexistence of pyrrhotite with hydrated clay minerals suggests that water on Bennu's parent body was not gentle water, but water engaged in dynamic chemical reactions where iron, sulfur, and other elements were continuously redistributed. Placed within the broader history of the solar system, these minerals indicate that during the early period, from about 4.56 to 4.4 billion years ago, water was not an exception. On the contrary, water was widespread within small bodies, penetrating primitive material and triggering long-lasting geochemical processes. This strongly supports the hypothesis that organic material and water were distributed throughout the young solar system before planets fully formed their structures and settled into stable orbits. More importantly, the hydrated clay minerals on Bennu reveal how water interacted with material, for how long, and to what extent. This information is crucial for scientists modeling planetesimal formation, understanding how heat and water interact within small bodies, and why some objects preserve primordial chemistry while others do not. In this sense, Bennu becomes a benchmark for comparison with other carbonaceous asteroids and with meteorites that have fallen to Earth. For the first time, we can study in detail a primitive object bearing clear traces of water that has never been exposed to Earth's environment. And as the mineralogical evidence grows ever clearer, the OSIRIS-REx mission transforms these ancient traces into living historical data here on Earth. Chemical analyses confirm that Bennu contains a rich collection of complex organic compounds, including numerous amino acids, nucleobases, and molecules bearing carbon, nitrogen, and oxygen the core elements of biology. These compounds do not appear randomly or chaotically. Instead, they reflect familiar chemical pathways, governed by thermodynamic principles and reaction kinetics. It is here that the hypothesis of chemical panspermia gains strong support, with carbon-rich asteroids and comets acting as delivery vehicles, transporting the raw building blocks of life to young planets. One key insight revealed by Bennu is the widespread nature of prebiotic ingredients. Rather than being rare anomalies, Bennu shows the opposite. In carbon-rich environments with past water and moderate radiation, these molecules can form naturally. From the perspective of the RNA world hypothesis, Bennu holds particular significance. Data from Bennu suggests that these components did not need to form at the same time or in the same place. Instead, they could have emerged in different environments, been preserved within asteroid material, and later assembled when delivered to a planet with more stable conditions. Rather than a closed system, Bennu suggests that Earth may have been continuously resupplied by carbonaceous asteroids during its early history, especially during periods of heavy bombardment. In this context, life is not the product of a single lucky moment, but the cumulative result of matter, energy, and time. However, there is no evidence that life ever existed on Bennu itself. There are no biological structures, no signs of metabolism, and no characteristic organization of living systems. No matter how abundant the molecules may be, they do not automatically become life. They require a stable environment, continuous energy cycles, and mechanisms of selection to cross that threshold of organization. Bennu provides the materials, but not the final context. Bennu also forces science to adjust its strategy in the search for life beyond Earth. Rather than focusing solely on present-day Earth-like planets, data from Bennu indicate the need to understand the entire chemical distribution network within a planetary system: asteroids, comets, moons, and impact-driven processes. And as the mineralogical evidence becomes increasingly clear, the OSIRIS-REx mission transforms these ancient traces into living historical data here on Earth. OSIRIS-REx approached a primordial asteroid, physically interacted with it, and returned to Earth samples that had never been touched by our planet's atmosphere, water, or biology. Launched in September 2016 under NASA's New Frontiers program, OSIRIS-REx followed a complex trajectory lasting more than 2 years before reaching Bennu in late 2018. Bennu's mass is so small that its surface gravity is only about 1/millionth that of Earth. Under such conditions, the very concept of landing almost ceases to exist. Even a tiny error in velocity could send the spacecraft rebounding back into space or result in an uncontrollable collision. Bennu rotates rapidly with a period of roughly 4.3 hours, and its asymmetrical shape creates an uneven gravitational field. Orbital measurements also show that Bennu is strongly influenced by the Yorp effect, in which solar radiation generates torque that gradually alters the asteroid's rotation rate over time. For OSIRIS-REx, this meant that every dynamical model had to be continuously updated because Bennu's surface was not a static platform, but a slowly evolving system. Before arrival, models had predicted a relatively smooth surface, with extensive areas of fine-grained regolith suitable for sampling. Reality proved dramatically different. Bennu turned out to be a boulder-dominated world, where large rocks prevailed and fine material was scarce. This forced the science and engineering teams to redesign their sampling strategy in real time during the mission, a true test of modern science's capacity for adaptation. The key to the entire mission lay in the TAGSAM technology, the touch-and-go sample acquisition mechanism. Instead of drilling or digging, TAGSAM operates on the principle of an extremely brief contact. OSIRIS-REx's robotic arm, more than 3 meters long, was designed to touch Bennu's surface for just a few seconds, while releasing a burst of compressed nitrogen gas to stir up material and drive it into the sample head. This method exploited Bennu's weak gravity. Material was not compacted, but easily lofted and captured. The mission's minimum goal was to collect 60 grams of material, a modest amount, yet sufficient for analysis in laboratories around the world. But on the 20th of October 2020, when OSIRIS-REx executed the touch-and-go maneuver, Bennu responded in a way no one had anticipated. Instead of resisting, the surface collapsed beneath the TAGSAM head, behaving like a layer of porous material. Sensors recorded the sampling arm sinking deeper than expected, while the nitrogen gas carried far more material than the original design had planned for. Faced with the risk of irreversible loss, the mission team made a decisive, time-critical choice to seal the sample head early, skipping some planned verification steps in order to prioritize preserving the collected material. Bennu's unexpectedly soft surface revealed that many rubble pile asteroids may be far less cohesive than previously assumed. A finding with major implications not only for planetary science, but also for future Earth defense strategies against potential impacts. Here, OSIRIS-REx did more than collect samples. It forced science to revise a fundamental assumption. After securing the samples safely inside its return capsule, OSIRIS-REx completed its final observations before departing Bennu in 2021. Throughout this phase, The spacecraft carried not only ancient material, but also a clear message. Humanity has entered an era of direct interaction with solar system history, no longer limited to passive observation. Yet the most severe challenge still lay ahead, transporting that fragile material across hundreds of millions of kilometers of space, re-entering Earth's atmosphere at extreme velocity, while preserving its chemical integrity. It is at this point that the OSIRIS-REx journey moved into a realm where every technical detail became a matter of survival for science itself. In September 2023, the sample capsule separated from its parent spacecraft and began re-entering Earth's atmosphere. The trajectory was calculated with extreme precision, because even a minor deviation could have sent the capsule into the ocean or subjected it to thermal loads beyond its limits. At the moment of re-entry, the capsule was traveling at approximately 43,000 kilometers. Friction with the compressed air ahead of it generated a plasma sheath, driving surface temperatures to around 2,700 degrees Celsius, heat intense enough to destroy most engineering materials ever used in aerospace. The survival of the Bennu samples depended on the phenolic impregnated carbon ablator, or PICA, heat shield. This was not merely a passive layer of protection. PICA functions through controlled ablation, carrying heat away from the capsule's core. During the brief minutes of re-entry, the outer layer gradually sacrificed itself to keep the interior, where the samples were stored, below 75 degrees Celsius. That threshold was critical because many organic compounds and prebiotic polymers can degrade or chemically alter if temperatures rise beyond it. In that moment, billions of years of solar system chemical history were entrusted to a material design both delicate and precisely engineered. The capsule landed safely at the Utah Test and Training Range, a desert location chosen for its high level of security control and biological cleanliness. From the very beginning, the Bennu samples were never allowed to come into contact with Earth's air. Any moisture, microorganisms, or dust particles could compromise analytical results for decades to come. As a result, from the moment of recovery, the capsule was placed into a sealed transport system and handled in a pure nitrogen environment, completely isolated from the outside world. Then an unexpected problem emerged, one that did not come from space, but from the Bennu dust itself, whose ultrafine particles had worked their way into screw threads and locking mechanisms within the capsule. Technical success at Bennu had created a new challenge on Earth. Engineers and scientists were forced to develop entirely new tools, precise enough to operate in confined spaces, gentle enough not to damage the material, and clean enough to avoid introducing any foreign substances into the analytical environment. All operations were conducted inside nitrogen-filled glove boxes, using specialized gloves and multi-layer contamination control procedures. The process of opening the capsule, initially expected to take only a few weeks, ultimately required about 3.5 months. Every grain of dust represented a fragment of 4.5 billion-year-old history. Trading speed for reliability was an ethical scientific choice, not merely a technical one. When the capsule was finally fully opened, the samples were sorted, weighed, and sealed individually. With a total mass exceeding 1 kilogram, the largest quantity of asteroid material ever returned by a U.S. mission. A portion was allocated for immediate analysis, while the remainder was placed into long-term storage, preserved as a scientific legacy for future generations, when analytical technologies will have advanced beyond today's capabilities. After Bennu, science enters a new trajectory, with the OSIRIS-APEX mission officially confirmed. The focus shifts to Apophis, a near-Earth asteroid about 340 meters in diameter that will pass extremely close to Earth on April 13, 2029, at a distance of just 32,000 kilometers, closer than many geostationary satellites. Unlike Bennu, Apophis is not a sample return target. Its scientific value lies in gravitational interaction. For the first time, humanity will be able to observe at close range how Earth's tidal forces act on an asteroid at full, real-world scale. Other carbonaceous targets, such as Ryugu, allow for direct comparison, what is universal in prebiotic chemistry, and what is unique to each celestial body. The more asteroids that are surveyed, the clearer the picture becomes. Primordial material is not uniform, yet it follows shared underlying rules. This sequence of missions also brings renewed attention to a concept once considered purely science fiction: space resources. Carbon-rich asteroids contain water and volatile compounds, potential fuel sources for future transfer stations. Metallic asteroids contain iron, nickel, and precious metals. At a deeper level, the post-Bennu future reflects a shift in how humanity views the universe. We are no longer merely passive observers, standing on Earth and gazing at the sky. With each mission, we become agents of measurement, gentle intervention, and growing understanding of the laws that govern extraterrestrial matter. This shift is scientific, but also existential. By learning more about asteroids, humanity is learning how to coexist with a dynamic universe, one where risk and opportunity always exist side by side. When viewed as a whole, from Bennu to Apophis, from Ryugu to Psyche, a pattern begins to emerge. Asteroids are not meaningless debris, but unread chapters of solar system history. Each chapter, adds a new perspective: chemistry, dynamics, resources, risk. Taken together, they offer humanity a chance to understand not only how planets form, but also its own role in that process, as a species capable of reflection, preparation, and choosing its future based on knowledge. The presence of nitrogen and oxygen-rich polymer compounds, along with sugar molecules such as ribose and glucose, on the asteroid Bennu has far exceeded NASA's original expectations. These were not mere accidental discoveries. They represent missing pieces in the larger picture of how the solar system formed. In the harsh environment of deep space, where radiation and extreme temperatures typically destroy organic structures, Bennu has acted as a resilient natural laboratory, preserving the most primitive ingredients of the universe intact for more than 4.5 billion years. From the perspective of planetary chemistry, the discovery of 15 types of amino acids and the full set of nucleobases that make up DNA on an extraterrestrial body has fundamentally reshaped our thinking. It confirms a profound idea. The precursors of life are not exclusive products of Earth's environment. On the contrary, they were already drifting through space long before our planet was forged in fire and cosmic dust. As the mission at Bennu comes to an end, we have brought back more than dry, black grains of dust. We have retrieved a key to an ancient source code. When we look at these unusual polymer compounds, or complex chains of sugar molecules, we are not simply looking into the past of an asteroid. We are looking into a mirror reflecting the origins of humanity itself. We no longer need to stare into the sky and ask, "Where did we begin?" Because the answer may have always been there, hidden within the silent journeys of objects like Bennu, traveling through billions of years of cosmic time. Thank you for staying with WUFO Space until the very end of this journey through the vast universe. If you found this video interesting and insightful, don't forget to like, share, and subscribe to WUFO Space so you won't miss our next cosmic adventures. Your support means the world to us and fuels our passion to keep exploring the wonders beyond.